This video is for those of you that have taken two completely different samples of something and you have looked at the average from each sample. So for example, let's say I looked at two different pizza chains and we'll call one of them brand D and the other one brand PJ. And what I want to find out is if those two pizza chains have significantly different mean saturated fat contents. So we're not looking at parts of a group, we're not looking at percentages, we're taking the values that we get from both of those samples and we're trying to find the average for each of those samples to see if one is bigger than the other. Okay, so because I'm taking two samples, that will kind of indicate to me which direction to go with the test that I want to choose. And since we are looking at averages instead of proportions, we won't choose the proportion test, we'll choose a t-test for means. Now, before I start, I need a hypothesis. Okay, so my null hypothesis and my alternative hypothesis should be centered towards my parameter of interest. You may have already calculated an X bar, which would be an average for the first sample you have, and an X bar that is the average for the second sample you have. However, this hypothesis should be centered around your parameter of interest. So from this sample, we really want to know about the true average fat content for these particular brands. Now, because I've run two separate samples, I should have two mean values in my hypothesis where I am comparing the mean from brand D to the mean from brand PJ. So I'm going to use subscripts to indicate which mean I'm talking about in which particular part of the problem. So the alternative should match, should look exactly the same with the exception of the equals. And the alternative should be what I'm trying to prove. Now, if you're trying to prove that one of them is bigger than the other one, if you were trying to prove that brand D had more fat, then you would use greater than here. If you wanted to show that brand D had less fat, then you would use less than here. But since this one is just asking me if they are significantly different, not really caring if one is bigger than the other, then I'm just going to use a not equals here for different. Okay. Now, in order to do any test on means, we do have to meet certain conditions. So I'm going to check those conditions really quickly. The first condition that I have to meet is that my samples were chosen randomly or that I did some type of assignment randomly. I'm going to assume these are random samples for your study. You should know that they are random. You can even list what type of random sample you chose because that is a requirement for your study. The second condition that has to be met for means is that this has to come from a normal curve shaped data set. Now, if your sample size is greater than or equal to 30, this is the only thing that you need to state. That assures me that this is coming from a normal curve. I think one of your assignment requirements is that you do have a sample size of 30. So if that's the case, you can stop right there. If for some reason your sample size is not 30, which in this case is my case, then you do have to check what's called a normal probability plot. Your calculator will do that for you. You do have to check it for brand D as well as brand PJ, which means I'm going to have to enter my information into the calculator. So if I go to Stat Edit and type in my information here, I have some old information up there. I'm going to go up to L1 and hit Clear and then come back down to wipe that out. And in L1, I want to make sure that I enter the data for whatever the first brand is that I listed in my hypothesis, which was brand D. So I'm going to enter 17 and 8, 12 and 12, 10 and 15, 8 and 7, 8 and 11, 10 and 11, 10 and 13, 5 and 13, and 16 and 11. And I missed my 16 right there. Okay, we'll span back through, just make sure that looks correct. And then in L2, I'm going to type in my PJ, which is 6 and 11, 7 and 3, 11 and 4, 9 and 5, 4 and 8, 4 and 5, and then 7, 5, and 9. Now, obviously, these two groups do not have the same amount of data, and that's perfectly okay in this case because there is no pair between these two brands. Like the 15 and the 4 right here that are across from each other, they don't have anything to do with each other. The 15 is from a completely different brand than the 4, and they have no association to each other. If they did, this would be a paired t-test, and you would need to watch a different video. But because these are two separate brands, nothing to do with each other, we are perfectly okay to have unmatching sets here. And to check the normal probability plot for each, I'm going to go to second y equals, which brings me to the stat plot. I'm going to hit enter on number 1. Make sure that it's turned on and that the final graph is chosen. This is your normal probability plot. And the first time through, I'm going to make sure that this is on list 1, which is second 1. When I hit zoom 9 to graph it, this appears approximately linear, which is going to tell me that this is a normal distribution. So all I would need to note here is that for the D, and I'm going to put approximately linear right here, but I'm going to go and also do this for PJ because they both need to be approximately linear. So I'm going to go back to second y equals, choose number 1 again. It should already be turned on and the last graph chosen, but I need to change my data list to L2. So I'm going to hit second 2 to do that. And now when I hit zoom 9, this one also appears to be roughly linear. So I'm just going to make a note here that they are both approximately linear, and that takes care of my normal condition. Now again, if your sample size was greater than or equal to 30, this is not needed. You could just stop right here. Your third and final condition is your 10% check for independence. And that is based on your sample size. I'm going to use my largest sample size here. So 2, 4, 6, 8, 10, 12, 14, 16, 18. If my largest sample size was 18 and I multiply that by 10, that's 180, and that has to be less than the population of all pizzas that I could look at. And I certainly feel like I have more than 180 pizzas that I could choose from. So my conditions are met because I had 2 samples and I was looking at averages, which is a t-test, and the data was not paired in any way. They had no association with each other. Then I'm going to run a 2-sample t-test. My calculator does that for me, so I'm going to go to Stat, over to Test, and I'm going to choose a 2-sample t-test, which is number 4. And it's going to ask me first, do you have the list of data, or have they already computed mean and standard deviations for you? We just have the list of data, and that's probably what you're going to have in your study. So I'm going to choose data. I'm going to let the calculator know where that data is located. We put brand D in L1, and we put brand PJ in L2. Your frequencies should always be 1. And then U1 is your alternative hypothesis, which in this case we chose not equal to. We are never going to pool, so choose no, and then choose calculate. And that is going to spit out a p-value for you. Now your p-value here is 1.14, but that does not make sense because this is a probability. Probability can't be more than 1. So we have this e to the -4 in the back, which means we have to move that decimal 4 places to the left. That is scientific notation. So that's truly a p-value of 0.0001. And because that p-value is less than a 0.05 alpha level that we typically test, then I am going to reject the null hypothesis. And that tells me that I have evidence of the alternative hypothesis. So I have evidence that the average fat content from brand D is different from the average fat content from brand PJ. Okay, so I reject the null hypothesis and I say, yes, there is a difference between these two brands. Now, to support that conclusion a little more, we can also run a 2-sample T interval, same type of computation, but we're looking at the interval instead of the test. So if I go back to stat, over to test, but this time scroll down and choose the 2-sample T interval, which is number 0. All of my data should already be in there from running the test. So we did data in L1 and L2. Frequencies are still 1. Make sure your confidence level matches the alpha level that you used in your test. So 95% confidence level lines up with a 0.05 alpha level because together they are 100%. We are not pooling, and we're going to calculate this confidence interval. And that comes out as 2.37 up to 6.45. And because we were looking for a difference between these two, 0 is not in my interval. 0 would be the number that indicated no difference. So because this is not in my interval, there is a difference. And we can even go far as saying this. Because every single number in this interval is positive, and I have a positive difference between the two. And if I look back at the order in which I wrote my hypothesis, if I looked at the mean for the D, which I listed first, and looked at the difference between that and the mean of PJ, in order for this difference to be positive, then the mean for the brand D would have to be greater than the mean for PJ. Otherwise, it would have been negative. So I can even say that brand D has a higher fat content. Okay, and I can even say by how much. They measured this, I'm assuming in grams. So I could even say that it has a higher fat content somewhere between 2.37 and 6.45 grams higher than the other one. It's somewhere in that interval.